When we start looking at electronic spectroscopy or vibronic spectroscopy with rotations, vibrations, and electronic states involved, we now get a combination of all three, and this is what's occurring in the ultraviolet and visible region of the spectrum. Now, you have probably done UV-vis spectroscopy before, and you won't see spectra that look like what I'm about to show you. And that's because if we do things in the liquid phase, things dissolved in solvents or whatever, we'll generally see all of this is happening, but we generally see a very broad peak that's mostly associated with just the electronic energy. And so this would be, for something dissolved in water or something like that, we usually get a very broad peak. But if we look at things in the gas phase, where now the molecules are not interacting with each other or with the solvent, we instead see, a very difference. We'll see individual peaks that are all part of this overall electronic transition. And so what we're talking about here, where we can actually see all these, this is what we call high resolution spectroscopy. And so to get started, we'll look at, what are the energies that we're considering here. So now our energies are all three. We have the electronic energy, we have the vibrational energy, and we have the rotational energy. So we've looked at the vibrations and rotations already. Those are going to be the same. And for the electronic energy, there's not a simple equation. So there's no simple expression that we can use. Basically, we have to solve the Schrödinger equation using computational chemistry to find what are the energy levels associated with all the different electronic states. And so computational chemistry is an important part of electronic spectroscopy to interpret what's observed for particular molecules. And so when we're looking at an electronic transition, so we've talked about selection rules in the past, the selection rule of delta V equals plus or minus 1 no longer applies. So the selection rule is delta V equals anything. You can have any possible change in delta V for electronic transitions. For rotational selection rules, it depends on the type of electronic transition, and we won't get into all the details of that. But the selection rule for vibrations is anything goes. But of course, what we'll end up seeing is that you won't see any possible combinations, and we'll discuss that in just a minute. Okay, so just like the vibrations have their associated rotational levels, the electronic states have their associated vibrational levels, and they have their right. So we're getting layers here, right? Layers of our different energies and types of expressions that we have. So let's define some terms that are used when talking about electronic spectroscopy. So we have nu tilde 0, 0. This is the energy to go from the V equals 0 level of the lower state to the V equals 0 level of the upper state. We have TE, with the tilde indicates this is in wave numbers. So this is the difference in the bottoms of the potentials. Between our two electronic states. So this is kind of, if we ignore the fact that there's 0-point energy and only consider the electronic contributions, this is the difference in energies. Then there is D0. This is the dissociation energy from V equals 0. So if the molecule is in its ground state, ground vibrational state. And then DE is similar, but it's the dissociation energy from the bottom of the potential, which the molecule can't actually reach, but is useful for bookkeeping. So let's look at, in the next video, we'll look at a figure to kind of show what, talking about these without something to look at is a little bit difficult. So in the next video, we'll look at a figure that shows what I mean by all these different potentials and different terms. So we'll look at a figure from your textbook.